Hello and welcome everyone to LFI Educates. From this topic onwards, you are going to prepare for your exams. So from here, listen carefully. We'll start from law of conservation of linear momentum. Law of conservation of linear momentum, it states like this: the total linear momentum of an isolated system remains constant when no external force acts on it. This law we call it as law of conservation of linear momentum. Now you may be thinking, what is an isolated system? Here you will focus it. Isolated system is that system in which other nearby objects, other forces, extra things should not come in between. You can see here one pen cap and one pen. When I am talking about these two, then my hand that is holding the pen and the pen cap, you'll have to neglect it. You'll have to think that it's not there. Suppose these two objects are coming and hitting like this each other. After hitting, what happened, where it went, there only we are focusing. Air resistance will neglect it. My hands here will neglect it. Only these two objects. Purely you have to think about these two objects. Then we can call this pen and the pen cap as an isolated system. That means in an isolated system, the total linear momentum always remains the same. It always remains the same or always remains constant. The meaning is that, suppose when I am talking about these two, before hitting, they are moving like this, suppose, before hitting, and after hitting, the momentum will remain the same. The initial momentum and the final momentum. Initial is before hitting, final is after hitting. What will happen? The momentum will never change, it will remain the same. That is the law of conservation of linear momentum. You can prove it like this from Newton's second law of motion. From Newton's second law, you can write force F is proportional to dp dt, rate of change in momentum, or you can use equal to also, because the value of k is 1 in SI system. So F is equal to, when no external force acts on the system, when this force, the external force that you are applying, if it is 0, then this dp dt also will be 0. You can keep in vectors also, no problem. So this will give you dp is equal to dt into 0 will come out to be 0. And dp means change in momentum, that is final momentum minus initial momentum. It will be 0, or final momentum will be equal to initial momentum, or we can say initial momentum is equal to final momentum. So this proves the law of conservation of linear momentum. This one you can write it as mv minus mu. mv is equal to mu. So initial momentum and final momentum both will remain the same. It will remain constant. I hope everything is clear. If you don't want to put this arrowhead, if you don't want to, while deriving, it's always good that you use scalar quantities. Without putting arrowhead also you can get the relation. Because a vector can be represented in scalar form. But a scalar quantity cannot be represented in vector form. That you have to know it clearly. Now let us see about the equilibrium of a particle. Equilibrium of a particle, I'll write down here. In mechanics refers to a situation in which the net external force, net means total, the net external force acting on a particle is zero. If the net external force acting on the particle is zero, then we say that the body will not move. Equilibrium of a particle means it will be in equilibrium state. Suppose let us take an example of a particle here, and this particle is being acted upon by two forces. Let us say F1 and the other one is F2. We know that towards positive x-axis this force is positive and this is negative, and both the forces, if they are equal, then the body will be in equilibrium. So F1 is equal to minus F2. Both the forces F1 and F2, they are equal and opposite, suppose. Then in that case, the net external force F1 minus, if you bring this side, will be plus F2 is equal to 0. So the net external force will be 0 and the body will not move anywhere. Suppose this is the body P. Then we'll say that the particle is in equilibrium. This is for two force system. If we take three force system, then these forces we call them as concurrent forces as well. Concurrent forces are those forces whose point of origination is the same. Suppose this is the point of origination, one force is originating this side and here this coming on the other side. For three force system you can do like this. Suppose this is F1, this is F2 and this is F3. You can take it like this. And in this case, what you do for three concurrent forces, we'll use our parallelogram law of vector addition. The diagonal representing the parallelogram will give you the resultant. This will be the sum of both F1 and F2, as you know. F1 plus F2. And this is F3. So if I write F3 as positive, then F1 and F2 together, their magnitudes are equal to F3. Then we'll be looking like this if they are equal. Then if you bring them F1, F2 towards your left hand side, then you have F3 here will become 0. Like this will come out for concurrent forces if it is more than 2. So all this represents examples for equilibrium of a particle. In this case also, the body will not move in any direction. It will remain in the same place. This is your body P and here this is your body P. But you must be sure that F1 and F2, if they are equal and opposite, then it will come to be, their net force will become 0. Here also, sum of F1 and F2 together must be equal to F3. Then only the net force will be equal to 0. If suppose F3 is bigger, then it will pull the body this way. If sum of f1 and f2 is more, then it will come this side. It won't come this other direction. But when we are talking about equilibrium of a particle, the body is not supposed to move. Then in that case, the net force must be equal to 0. Net force must be equal to 0. In that case, f1 must be equal to f2 and f3 must be equal to f1 plus f2 together. This force and this force must be equal. That we call it as equilibrium of a particle. So it's very easy to remember. Only you have to know that the net force acting on the particle must be 0. Then the body will be in equilibrium. It will not move any side. It will remain in the same place. Now let us see Lami's theorem. According to Lami's theorem, if three concurrent forces F1, F2 and F3 are in equilibrium, then F1 divided by sine alpha is equal to F2 divided by sine beta equal to F3 divided by sine gamma. Diagram will look like this. Suppose this is the particle P, three forces are acting on it, F1, F2 and F3, and here F1 by sine alpha means opposite of F1 the angle is alpha, F2 by sine beta means opposite of F2 sine angle is beta, and opposite of force F3 the angle is gamma. This theorem we call it as Lami's theorem. Now let us prove and see the proof of the theorem. We'll use the law of sines, and we know that for concurrent forces the particle is in equilibrium. The condition is that F1, F2, F3 are in equilibrium, and if it is in equilibrium, in chapter 4 we learned that we can represent with the sides of a triangle. Suppose this is F1, this is F2 and this is F3. So if all the forces are in the same order, then the net resultant force will be equal to 0, or the net resultant vector will be equal to 0. Now let us see the angles here. Between F1 and F2 the angle is gamma. Between F1 and F2 the angle is gamma. One force is going this side, the other force is going this side, so the angle here is gamma. The angle between F2 and F3 is alpha. F2 and F3 is gamma. So I'll extend this one, is moving this side F2 and this F3, the angle between them is gamma. And then, the angle between F2 and F3 is alpha. This is alpha. And the angle between F1 and F3 is beta. F1 and F3 is beta. F1 is moving this side, so F3 I can extend this way, then I can get here beta. Now after getting the angles from the diagram, you can get the inner angles. This angle will be pi. Pi means 180 here. Pi minus alpha. Linear pair should form. Total must be equal to 180. And this angle will be pi minus beta. And this angle will be pi minus gamma. Then we can prove by using law of sine. By using law of sine, F1 divided by sine, opposite of F1 angle is pi minus alpha, so it will be sine pi minus alpha. This is your law of sine. This is F2 divided by sine pi minus opposite of F2, it is pi minus beta. Pi minus beta. Opposite of F3, you have the angle pi minus gamma. Sine pi minus gamma. Opposite of F3, you have this angle pi minus gamma. Now only one step you have to do. Sine 180 minus theta is equal to sine theta. That's all. F1 divided by sine alpha is equal to F2 divided by sine beta, that is equal to F3 divided by sine gamma. Since sine pi minus theta is equal to sine theta. That's all. Like this, you can simply get the Leibniz theorem from the law of sines. Both are the same law. The only difference is that Leibniz theorem, it is used for concurrent forces, particularly one vector quantity only. There is 4 forces, and your law of sine is applicable to all the other vectors. Let us do one simple numerical. You can see here one load is hanging here, 4 kg weight load. It is hanging from these 2 strings. You can see here, one is given tension T1 and one is given tension T2. This type of diagrams are called free body diagrams as well. You need to do more numericals related to this free body diagram method. Here you are asked to find tension T1 and T2 in the strings. So what you have to do is, when you do the solution, you will redraw the diagram nicely. These are the rigid supports. This is the ceiling, you can think like that. Then here you have the wall. One wall is given to you. Then one string kept like this, T2. Tension is T2. And one string is given like this. This is T1. And one load is hanging. The load weight is given as 4 kg weight. Now this one T2 is already in the horizontal direction. T1 is not in the horizontal direction nor in the vertical direction. So you need to resolve this T1 first. So let us do like this. We'll resolve it into, here the angle at this region it is 60 degree between T1 and the ceiling. So this angle also will be 60 degree. If you resolve it, then you know how to resolve. This is base, this is hypotenuse, so this one will become T1 cos. Cos theta is defined as base by hypotenuse. Like that, one component of a vector you will get along the horizontal direction, and one component you will get along the vertical direction. If one component is T1 cos theta, the other component will be automatically T1 sin theta. If you complete this one up to here, you can get a 90 degree. This is opposite side and this is the hypotenuse. So it will give us T1 sin theta. So you write like this, resolving T1 into its components. Number 1, T1 cos 60 degree along the horizontal direction, and one will be T1 sin theta. This is sin 60 degree. Angle here you know, this is 60 degree. So we'll write here 60 degree, T1 sin 60 degree along the vertical component. So these are the 2 components of the vector, that is T1. Now here By looking at the diagram, you can make out T1 sine 60 degree, because the load is neither going down nor coming up, so it is balanced force. Now you are using concurrent forces. T1 sine 60 degree is equal to, or equilibrium of a particle. T1 sine 60 degree is equal to 4 kg weight. So first we'll write T1 sine 60 degree is equal to 4 kg weight. Kg weight, if you change into newtons, it will be 4 into 9.8 newtons. Like this you can change it. Then T1, we don't know the value. Sine 60 is root 3 by 2. It is equal to, you can multiply this. 4, 8 4s are 32, 3 in hand, 9 4s are 36, 39, 39.2. So T will be 39.2 divided, multiplied by 2 divided by root 3. So this is your T1. So on calculation, T1 is equal to 2 to the 4, 9, 2 9s are 18, 8, 1 in hand, 2 3s are 6 plus 1 is 7 after decimal 1 digit. Then you have here root 3. Root 3 you can rationalize it. Root 3 into root 3. So it will give us 78.4 into 1.732. This is the value of root 3. Root 3 into root 3 is 3. Then you can multiply and divide to get the final answer. 732, 78.4, 8, 12, 2, 1 in hand, 7 4 28, 29, 2 in hand, 4, 5, 6, 16, 6, 1 in hand, 24, 25, 2 in hand, 56, 57, 58, 5 in hand, 8, 8, 5, 30, 7 to 14, 4, 1 in hand, 21, 22, 2 in hand, 49, 50, 51, 5 in hand, 7 7 plus 5 is 12, 8, 8, 9, 18, 8, 1 in hand, 14, 15, 16, 17, 7, 1 in hand, 3, 4, 5, 3, 1. After decimal you have 4 digits. So you write 135.7888. Then divide it. 3 4s are 12, 3 5s are 15, 3 2s are 6, 1 8, 3 6 are 18, 3 2s are 6, and it will go on. 2 less than 5, leave it. Tension means force, so SI unit will be in newtons. Like this you can find out T1. Then T2 to find out, you can use this relation. Here where you have redrawn T1 cos 60 degree is equal to T2. For the second one, if I do it here, T1 cos 60 degree is equal to T2. T1 value you know. Just now you found out 45.26. Cos 60 is 1 by 2 is equal to T2. 2 you can cancel. 2 2s are 4, 2 2s are 4, 2 6 are 12, 2 3s are 6. So T2, the tension is 22.63 newtons. Like this you can calculate it. Now let us study about the apparent weight of a man in a lift or elevator. Let us suppose, or let us consider a man of mass M standing on a weighing machine placed inside the lift. Suppose this is your lift. Let us consider this as the lift. The weighing machine is placed. Suppose here we are taking somewhere at the center, but we know that the weighing machine we place at the bottom of the lift. Let us take this point as G. Then the actual weight of the man will be mg, mass into acceleration due to gravity. Gravity of the earth pulls down. This will be the actual weight. That will be shown by the weighing machine. And that will be equivalent to the normal reaction. That is R. So the person will not float, will not go up, won't come down, it will remain the same place. This mg value and R value both will be equal. It will be balanced. So placed inside the lift, the actual weight of the man will be mg. That will be shown by the weighing machine. Which will be equal to the normal reaction R. R is the normal reaction. Now this normal reaction also we call it as the apparent weight of the man. The man, how he feels. Now we'll take different situation when this lift comes down with some acceleration downside. How the man will feel. Will he feel weightlessness, or will he feel that his weight is increased, that you are going to study? Or when the lift goes up, then what happens to the man, how he feels? The feeling will be given by this normal reaction. That's what we are going to study. Here R is the normal reaction is the apparent weight of the man. Here R is the apparent weight of the man. That's what we are going to find out here. We are going to study apparent weight of a man in a lift. Let us see one by one. Case 1. When the lift is moving upwards with acceleration A, suppose. This diagram itself will take it for the first case. Which side the body is moving, you will see R. The body is going up. The lift is moving up. So you will take R minus mg. Which side it moves, that side will take first. R minus mg. If the body is coming down, the lift is coming down, we will take mg minus R. That is the technique that you have to know. The body is moving up. So R will be bigger than mg now. So R minus mg, that will be equal to the mass of the man. This is the extra force that the lift is providing to the man. That is mass into acceleration, that is the extra force. So R is equal to mg minus, if you bring this side, it will become plus ma. So earlier when the lift was not moving, R was equal to mg. Now R is equal to mg plus ma, means extra force is added up to the apparent weight. So the man will feel heavier. We can even write like this, G plus A. So when the lift moves up, with some acceleration, the apparent weight will increase. the apparent weight will increase. Now let us see the second condition. When the lift, case 2 I am writing here, when the lift is moving downwards with acceleration A, then what happens? Let us see. You will redraw the diagram, but this time acceleration is not upside, it is downside. If it is downside, then here the body is moving down, so mg is bigger than r, so we write mg minus r. We write here mg minus r is equal to mass of the man into acceleration of the lift. So here what you get is minus r is equal to minus mg plus ma. If you change the sign throughout left hand side and right hand side, minus will become plus, then minus will become plus, and plus will become minus. In this case you get r is equal to mg minus ma. On m if you take common, it will be g minus a. So you can see here clearly, before the lift was moving, r was equal to mg. Now it is r is equal to mg is reduced by ma. So the man will feel that his weight has decreased. So he will feel that his weight is lost. So when the lift moves downwards with some acceleration, the apparent weight will decrease. When the lift moves downwards, the apparent weight will decrease. Move downwards with acceleration A. So you must be very sure that there is some acceleration. The lift must have some acceleration. Then the apparent weight will decrease. That is the second case. Let us see the third case. Case 3. When the lift moves either upward or downward without any acceleration, that is with the same velocity throughout its motion. When the lift is moving upwards or downwards without acceleration, then if there is no acceleration, acceleration will be 0, upside or downside. Suppose acceleration is 0, then in that case you can take either of the one, r minus mg or mg minus r, both will be same because m into a, the force exerted by the lift is going to be 0. A is 0 here, m into 0 will become 0. So in that case, if you write mg minus r or r minus mg, if it is moving up, take r minus mg. If it is moving down, we'll take mg minus r. That will be equal to 0 here. This will become 0. Mg minus r will become 0, and in that case r is equal to mg. So it will be the case when the lift was not moving. When the lift was not moving, r and mg both were equal. Here we have seen that will be shown by the machine, which will be equal to the normal reaction r. Mg will be equal to r. So if there is no acceleration, then the apparent weight does not change. When there is no acceleration, the apparent weight remains the same. Now, lastly, we'll study the fourth case now, case number 4. When the lift is moving downwards, with acceleration due to gravity of the earth, acceleration due to G, acceleration due to gravity G of the earth. Suppose the lift is coming down, falling freely, that means coming down with acceleration due to gravity of the earth, then it is falling down freely. Then what happens? mg is bigger this time, coming down, mg minus r will become, in place of ma it will become now g. So in such a case, minus r is equal to 0, mg can cancel out, or we say r is equal to 0, the normal reaction will become 0, the apparent weight of the man will become 0. When it becomes 0, that is the condition of weightlessness. When a man falls freely due to acceleration due to gravity of the earth downwards, then he will feel that he does not have any weight. That we call it as weightlessness. This is the condition of weightlessness. The apparent weight r is equal to 0 indicates the case of weightlessness. So all these conditions you might have experienced. Suppose you are in a flight, when the flight takes off, it goes up, then you feel that the weight is becoming more, the apparent weight increases. When the flight comes down, takes landing, then we feel that our weight has become less, becomes less. But if an object, like person those who do free fall, those who jump from a higher altitude from planes, then they will feel that their weight is 0. Weightlessness will be felt, the weight will become completely 0. Thank you and have a nice day. Stay tuned with LFI Educate.